So last video we looked at a few things with the Young experiment, that kind of stuff. We're going to look at the wave, and we're going to practice some more with that, but we're going to look at some more wave nature of light type stuff. But first I'm going to show you this little bit of a video that I found on YouTube for something that I was showing you in the lab as well. One of my favorite things for the wave nature of light, and that is polarization. Now, here we have a guy with a pair of sunglasses looking at the screen of a phone, and we'll played a little bit here. And when he has like that, no big deal, but then he turns it sideways, it goes black. And that's because of polarization. And polarization is a great example or demonstration of the wave nature of light. So if you turn the phone back, you'd see the screen again, but now it's perfectly black. And some of you guys know about polarized sunglasses. Some of you guys probably have polarized sunglasses as well. But let's look a little bit what polarization actually is. And it's kind of cool because, you know, he takes the phone, you can't see absolutely anything. And he tries a couple other phones as well, and he turns them sideways, and the things change. This one does not because it's not polarized. But we're going to show you how polarization is. It's great little proof of the wave nature of light once again. So if I just sort of quickly explain how polarization works. If you got like a lenses from like glasses or something like that that's polarized, and it looks like it's gray or black, whatever it is, but it actually isn't. If you could actually zoom in really, really far, you'd actually see it. There's like microscopic lines etched to it, and that's polarization. And the difference between regular glasses and polarized glasses is that regular glasses just sort of haze everything out, sort of like tone down everything. But polarized glasses actually block stuff. And I'll sort of show you what I mean by that. Suppose you have like a wooden fence with a whole bunch of vertical boards. Okay, and then what you do is you actually remove one of the boards, something like that, and then what you do is you take a rope, and you take the rope and you put the rope through the opening in the boards, maybe to the other side. And what you do is you wiggle the rope. Now, if you wiggle the rope up and down, those waves can easily go through the opening in the board. But if you wiggle the rope sideways, it'll slam into the boards and get stopped. And that's the basic idea behind polarization, how polarization works. Polarization will allow waves to go in one direction, pass through, but it blocks them going the other way. So right now, like these glasses right here, they would let waves going up and down through, but waves going side to side would get blocked. And that's the idea behind polarization. So when you have two things that are polarized, let's get rid of that a little bit. If you have two things that are polarized, for example, he had his glasses like this, and then he had that phone screen, and when they were lined up like this, it was fine. You could see everything, and phone screens are often polarized. But then when he rotated the phone 90 degrees, well, now instead of it being parallel, now the lines are perpendicular to each other. So when these lines are perpendicular to each other, they get blocked. If you could actually magnify it when it was set up like this, the lines would actually almost look like a waffle type pattern, or sort of like a bug screen in a window. And when the light is trying to get through, the vertical part is being blocked, the horizontal part is being blocked, and the light is just flat out blocked, and that's why it looks black. But when you turn them back the other way, then the lines are parallel and some of it's able to get through. So that's how polarization works. And this can only be explained if light travels as a wave. If light travels like a bullet, the bullets would just go right through the holes and get toned down, but bullets will still make it through. Well, no, polarization doesn't work that way. Polarization is really common for any kind of LCD screens, certain types of glasses, more expensive glasses, which really help to cut down things like glare and stuff like that, as well as a bunch of other things. But that's the basic idea behind polarization, and that's how that little thing actually worked. Okay, so I love polarization. And again, if you're in my lab, I've got polarization films and lenses, and I could show them this to you. It's really, really, really cool. And you may have noticed it yourself if you happen to have polarized sunglasses and you look at your screen, like the color changes a little bit and stuff like that. That's all from polarization. So again, it's a great proof that light travels as a wave. After the Young experiment stuff that you guys have done, it's another great little proof and application that's used for tons of different stuff. Okay, so let's get rid of this, and we are going to practice some more of the Young experiment a little bit with you guys and show you how that all can play into what you guys have been working to as well. Okay, so let's look at some more Young experiment setups and see what we can do. So here, let's set up some slits. You guys looked at what happened, the 2 slit experiment, stuff like that. We're going to send some light through here and make an interference pattern like you guys have done before. So we're going to have some light coming in, something like that. We'll make, go to color. Okay, have some light coming in, and it's red light. Okay, so we'll say it's some nice red light coming through, and we'll get a nice interference pattern, something like this. Da-da-da. Okay, all right, very good. And let's say the openings are 380 micrometers apart. Let's say the screen is 5.4 centimeters away. And let's say the distance from here to there is 0.28 millimeters. And what I want to know is, what is the frequency of the red light? Well, in order to find the frequency, I need to know the wavelength, and the Young experiment, Young setup is great for finding wavelengths. So let's see what kind of measurements I have so far. Well, let's see, the 380, that is my D value. The 5.4, that's my L value. And I got that 0.28, which you might think is the Y, but that's not the Y value. That's a few Y values put together, because that distance is Y, that distance is Y, and that distance is Y. This is actually 3 Y values put together. So to find my Y value, I need to take this and divide it by 3. So if I take that and I divide it by 3, my Y value would then be 9.33 times 10 to the negative 5 meters. There's my Y value. Okay, so I've got my D, I've got my Y, I've got my L value, so I can use those to find my wavelengths. Let's find the wavelength. Lambda is dy over L. I can find the wavelength of my red light. So punch the values in, watch out for the micro prefix, the centi prefix. This one's no good, that's just good to go. It's got the no prefix on there, so there's nothing there to worry about. Put the values in and calculate your wavelength. And you should get around 6.57 times 10 to the negative 7 meters, around 657 nanometers, which is red. Red's around, high 6s. It's max out around 7, but it's around mid-high 6s. Low 600 is orangey, and this would be a nice red light. So there's my wavelength right there. Okay, so once I have the wavelength, I can calculate my frequency. Frequency is just the wave equation, speed divided by wavelength. I've got the speed of light, that's fine. I've got my wavelength, divide the 2 out, and we should get around 4.6 times 10 to the 14 hertz, and that'll be the frequency of the light, the red light coming into my setup. Okay, well, let's see if we can find something else here. Let's see if we can find a little geometry here. Let's go with right here. I want to know what is the angle to the X right there. Okay, so what angles? We look at the geometry a little bit of this as well, and finding angles. What is the angle to the X value? So center line, something like this. What is that angle? Okay, so this is where you can use tan theta if you want, or you can use the sine function as well. We've used that one before. So if I just did the sine expression, sine theta is equal to, there's n lambda over d, but in this case, that is at a minimum right there. That's a minimum location. So instead of n, I want to use the n plus a half lambda over d, because we want to shift that wavelength by half. So again, I'm going to be careful with the n value. This would be the first minimum right there, second minimum, third minimum. It's a third minimum, but the third minimum, remember the fringe number would then be 2, because remember the fringe numbers start counting at 0. So 0 plus a half, 1 plus a half, 2 plus a half wavelengths difference. So my fringe number would be 2 in there. Okay, so I've got the 2. I know my lambda already from before, the 657. My d value is given 380. I can then calculate the theta. Just don't forget to inverse sine it. So if we do all that, we plug everything in, we should get an angle of around 0.25 degrees. Okay, all right. So let's get rid of this and let's try another Young experiment type question. All right, so let's try this one. We got 1.75 times 10 to the 16 hertz light coming into a couple openings, making an interference pattern. Bright spots are 0.187 millimeters apart, 14 centimeters for it to go. And we're going to find out how far apart are the openings. So let's see if we can find that. Okay, well, if I go back to my basic expression, D would be lambda L divided by Y. Let's see what I've got. I've got the Y value right there. That's fine. The 14 here, that's my L value. But I don't have my wavelength. I've got the frequency, but I don't have the wavelength. So I just have to find my wavelength, and then we will be good to go. So no problem. If I find my wavelength, of course, wavelength is C divided by frequency, which I have the frequency. So if I do 3 to the 8 divided by the 1.75 to the 16, I will get a wavelength of about 1.71 times 10 to the negative 8 meters. So that is actually pretty small. That's like only like 17 nanometers, so that you couldn't see. That's like ultraviolet type light. So all good. All right, so let's put the wavelength value in there. We got the L value, to watch out for the centi, and we put in the Y value, and we can punch it all together, and we can get our D value. So if we do that, we can find that our openings are about 1.28 times 10 to the negative 5 meters, or I guess that'd also be like 12.8 micrometers apart. So that's how far apart the openings are. Okay. All right. Now let's build on this a little bit. How about this? What would if we go at an angle of 0.16 degrees, what would the intensity of the light be? Would it be maximum, minimum, in between? Let's see what kind of intensity we've got or brightness we have at an angle of 0.16 degrees. Okay, well, we can bring out the sine theta expression again. We've used that before. So sine theta is equal to something lambda over d. Now that's something, is it n? Is it n plus a half? Like, we don't know what it is, so we got to find out what it's actually going to be. So let's find out what that question mark would actually be. So the question mark, of course, just rearrange this a little bit, would be d sine theta divided by lambda. So let's see what we get for a question mark when we punch that all out. See if it's integer plus a half. Let's see what we get. So if we do that, we get around, well, give or take, around 2.1. So about 2.1. So that's actually really, really close to an integer. So this really, really, really close to a maximum. So it'd be really, really close. And that would be the fringe number, so 2.1. So this guy right in the middle, fringe number is 0. This one's got a fringe number of 1. This got a fringe number 2. So we're probably looking at like right there, just not exactly in the middle of the dot, but just a little bit further than the dot. So it's really, really close to a maximum. It's pretty bright light at that location. So that's how that sort of all pieces together. Okay, so there's a couple more examples of how to do the Young experiment and how polarization works, and how polarization again proves that light travels as a wave.